Hello everyone, welcome back to Abstract Algebra. Today we're going to talk about homomorphisms. Previously we've talked about normal subgroups, and today we're going to extend the notion of isomorphism to other types of maps, and we'll see at the end of the lecture how this actually relates to normal subgroups. So just as a reminder, recall what an isomorphism is. So an isomorphism is a map from a group to another group such that one, phi is a bijection, and two, phi respects group structure, which means that for every G1 and G2 in G, we have that phi of G1 star over G with G2 is phi of G1 star, that's the multiplication in H, times G2. And these are very important maps, as we saw, because they allow us to compare groups to see when two groups are essentially the same group. But there are cases where there are maps that respect the group structure. There are not bijections, that they still give us a lot of very useful information of how two groups are similar. Let me start with an example that we saw, an example of something that is a group isomorphism. Remember that if G is an infinite cyclic group, let's say that G is generated by one element G, then the map that sends the integers to G such that n is going to G to the n is an isomorphism. Okay, and that told us that every infinite cyclic group is isomorphic to the integers, which was just one interesting result. And this map is bijective and it respects group structure, but this map appears in many other cases. In all cases, we have a similar map. So if G is any group and G is any element of G, we can define the same map that goes from the integers to G and sends n to G to the n. I can define that map. That map is well defined, but it will not be a bijection in general. However, it always respects group structure. So it respects group structure because if I always do any n and any m, any two integers, that will be G to the n plus m, which by the laws of exponents, that's Gn star G to the m, and that is phi n star phi m for any n and m integers. So it respects group structure, but it is not always, I'm going to write it, not always a bijection. However, even if it's not a bijection, it gives us some important information. For example, suppose, let's just do something very concrete. Suppose G here is Z modulus X, and little g is just 1 mod 6. Then I do have a map that goes from the integers to the integers modulo 6 that sends any integer to the multiples of 1. So it's just going to n modulo 6. This is a map that respects group structure such that n plus m is actually congruent to phi of n plus phi of m mod 6. But this is not injective, as any integers that are congruent modulo 6 will go to the same place. So for example, phi of 0 is the same as phi of 6, or phi of 1 is the same as phi of 7. It is not injective. Still, it tells me something like the fact that Z modulo 6 is cyclic because there is a generator that cycles over all of them. It is surjective. This map, it is surjective, but it is not injective. Still, as I said, this tells me something about the group Z modulo 6 and the group Z. Here's another example. I can write now G to be Z cross Z, and I'm going to take G to be 1, 0, and now I'm going to write a map that goes from the integers to the integers modulo, the integers cross the integers, so the direct product that sends n to the multiples of that one, so it's going to go to this element. So this one, it is also preserves group structure, like before, but it is not surjective. It's injective, but it is not surjective. This is not true. That is, it's not surjective because, well, I obviously I can't get anything like 0. M is not in the image. It's not in the image of phi. But still, it tells me something interesting, which is that this group contains, because this is an injection, so Z is injected into here. So that tells me that the integers are in here somehow, so that this does contain a copy of the integers. So that is important information about the group G. So because of all of these things, we define maps that preserve group structure. Those are going to be called homomorphisms, and they are important on their own right. So let G and H be groups. A function, let's say psi from G to H, such that for all G1 and G2 in G, we have that psi of G1 star G, G2 is the same as psi of G1 star H. Psi of G2 is called homomorphism, is called homomorphism. Homomorphism, which, by the way, this means same, and this is shape. So we're saying they're homomorphic if somehow they have the same shape or similar shape. And let me give you an example of a homomorphism. So now a homomorphism that I'm going to use often. So all the other ones that I've showed you, let me actually start with that. G any group and G in G, then the map that sends the integers, the other way around, the map that sends the integers to G and sends n to G to the n is a homomorphism, because as we have seen, it preserves group structure. A more interesting homomorphism is the following. Now let G is going to be GL2 R, which is the 2 by 2 matrices. So A, B, C, and D are real numbers, and they have non-zero determinants. So AD minus BC is not zero. This is a group under matrix multiplication, and I'm going to put H to be R star, so non-zero reals. And I have a map that is going from GL2R to R star given by a matrix is going to go to its determinant. Then you see that, first of all, this is well defined. So 0 psi is well defined because if A is in GL2, then psi of A is the determinant of A. It is precisely, if A is the matrix A, B, C, D, it is precisely the quantity AD minus BC is non-zero, and therefore psi of A is in R star. So the map sends matrices to where we said they go. Now, it is a homomorphism because let's see what happens. So if A and B are matrices, then what is psi of AB? The product, that will be the determinant of the product. But now a well-known equality is that the determinant is multiplicative. The determinant of a product is the product of the determinants. So this is the determinant of A times the determinant of B. And the determinant of A is psi of A, and the determinant of B is psi of B. Therefore, psi is a homomorphism. I will abbreviate carefully homomorphisms as HOMs. Okay. However, psi is not an isomorphism. So note, psi is not an isomorphism because although it is surjective, it is not injective. So let's see that, first of all, psi is surjective. So if I have some, let's say A, some non-zero real numbers, non-zero real number, I want a matrix whose determinant is exactly A, but I can say, well, the determinant of A001 is A, and therefore psi of A001 is A, and therefore psi is surjective. However, psi is not injective because there are many other matrices whose determinant is A, for example. So for any A, I have that the determinant of A001 is the same as the determinant of 100A is the same as the determinant of 0 minus A10, for example. That is all A, and therefore psi is not injective. So it is not an isomorphism, but it is still a homomorphism. And this map will be interesting. We'll see why in a moment, because of the properties of homomorphisms. It's going to give us a bunch of interesting stuff. It's going to tell us that information about GL2 that we didn't know before, just because there is a map down to R star, it will give us important information about GL2. Okay, so let's prove some properties about homomorphisms. Here are the properties I want to prove. So let psi from G to H be a homomorphism. Then the following are true. First, psi of the identity, the image of the identity is the identity. This also happened for isomorphisms, and the same reason will apply here. Two, for any G in G, the image of the inverse of G is simply the image of G inverse. We also have that now if J is a subgroup, then we also have the psi of J, the subset that you get when you send all of J over, is a subgroup of H. And now that starts to be interesting, because when we know one group, so if we know the subgroups of G, I can send them over and find subgroups of H. Not all of the subgroups, but a number of subgroups. For the other way around also works. If K is a subgroup, then the set theoretic inverse of K, so every element of G that maps to K is a subgroup of G. And 5, and more importantly, is that if K is normal in H, so if it is a normal subgroup, then the inverse image of K is normal, is normal in G. We knew from 4 that it is a subgroup, and now it is also normal. And now that is really interesting, because normal subgroups are hard to come by. When G is non-abelian, then it is hard to tell what groups or what subgroups are going to be normal, and this gives me a way to construct normal subgroups of G if I have a homomorphism. And in fact, we will do that a lot whenever we want to prove that some subgroup is normal. We will construct a homomorphism, and such that the pre-image of some group is the group that I want to prove that is normal. So let me prove these properties. So first of all, part 1, we have that psi is Hom, and I want to know how much is psi of the identity of G. Let's call that H. By the properties of the identity, psi of the identity is identity times identity, so I can double it up like that. This is something we use very often in mathematics, that 0 is 0 plus 0, and that 1 is 1 plus 1 times 1. Those silly equalities actually give you always many times a trick to do proofs. So in any case, identity is identity times identity, and now I can use the property of homomorphism to prove that psi of the product is the product of the psi's. So this is the image of E, the star, and this is the star in G, this is the star in H, that that is going to be psi of E times psi of E. Now, psi of E itself is H by definition, how we defined psi of EG. So this is H times H. So what I got is that H is H times H, and therefore just multiply by H inverse on both sides. What I'm going to get is that E equals H. Namely that this is the identity in H, so that the identity in G maps to the identity in H. Okay, so that proves 1. For 2, I can do a similar thing. So let G be in G, and consider how much is psi of G inverse. That's what I want to do, but I'm actually going to start from psi of the identity, because now I know from part 1 that that is identity, and I'm going to rewrite the identity. A third equality here that is very useful is that 1 is A times A inverse in the real numbers, for example, or in any group you have some equality like that. And what I can do now is write the identity as G times G inverse in G, and therefore now I can use the property of homomorphism to write that this is psi of G star psi of G inverse. And since that is the identity, then I can now see that the inverse of this element is this element. Or namely, if I multiply both sides by the inverse of this element, what I get is that the image of the inverse is the inverse of the image, which is what I wanted to check. Okay. What is the third property? Let's go back to the statements. The third thing I want to prove is this, that if I have a subgroup, the image is a subgroup. Part 3, let J be a subgroup. And I want to let K be the image of J. I want to show that K is a subgroup of H, and remember that criteria for something being a subgroup is the following. For every K1, K2 in K, I want to show that K1, K2 inverse is also in K. So let's do that. Let K1 and K2 be in K. And what do we know about K? K is the image of J. Thus, there are some J1 and J2 in J such that Ki is psi of Ji, right? That each Ki is in the image of psi. So there are some J's that map to the K's. And then let's see how much is K1, K2 inverse. K1 is psi of J1, and K2 is psi of J2 inverse. But by the previous property, I know that the inverse of a psi is a psi of the inverse. So this is psi of J1, psi of J2 inverse. And now I can use the property of homomorphism to put those two psi's together into one, J1, J2 inverse. But now this, because J is a subgroup, we know that this is in J. And therefore, this element belongs to psi of J. It's in the image of J, but the image of J is K. And that's what I wanted to check. I wanted to check that this is in K. That proves that since this was for any K1 and K2, that means that K is a subgroup. Great. The fourth one is the inverse image of a group, of a subgroup. So now let K be a subgroup, and let J be the inverse image of K. So what does that mean? Those are all the G's in J such that psi of G lands in K. Okay, and we want to show that J is a subgroup. Is a subgroup of G. So what I want to show is that for any J1 and J2 in J, I do have that J1, J2 inverse is in J. So to do that, let J1, J2 be in J. J is the inverse image of K. So there are K1 and K2 in K such that the Ki's are precisely such that such a psi of J I lands in Ki in K. That's what being in psi inverse of K means. And now let's see how much is J1, J2 inverse. I want to show that this is in J, so it has to be in the preimage of K. So let's see if we can prove that. J1, so because I want to see that this lands in K through psi, all I need to check is where this lands. I hope it lands in K. This, by the properties of homomorphism, this is psi of J1, psi of J2 inverse. Again, by one of the properties we've proved, this is psi of J2 inverse. And this is psi of J1 is K1, psi of J2 is K2 inverse. But this, each one of those is in K, so this is in K because K is a subgroup, and therefore this is in K, and that tells me that J1, J2 inverse is in the inverse image of K, and therefore my J is a subgroup, which is what I wanted to check. And last but not least is the normality. So now 5, if K is normal in H, then J, the inverse image of K, is normal in G. Okay, so let's try to prove that. First, let's recall what normal means. Recall that K is normal in H if and only if for any age, let me write it like this, for all ages in H, we have that HK is the same as KH. The left coset HK and the right coset KH is the same, but we prove that this is the same as for all H's in H, HKH inverse is the same as K, and we actually prove that this even only if HKH inverse is contained in K. And now this is the property that is going to be the most useful and that we're going to use when we prove normality. So I want to show, in fact, that J is normal in G. So what I want to show is that for all G in G, we have that G inverse is contained in J. Okay, so that is what we're going to try to show. So let's assume that K is normal in H, and now let G be in G and J be in J. Now J is the inverse image of K, so there is some K in K with psi of J equals K. Okay, we know that. And now consider the element G, J, G inverse. I want to show that for any J like that, I want to show this containment. So for any J, for an arbitrary J and for an arbitrary G, this has to be another element of J. You will be in J if you map down to K when you use psi. So I'm going to send this via psi and see what I get. By the properties of homomorphism, I can break this as psi of G, psi of J, psi of G inverse. Now that psi of J is K, so I can write this as, let's write this to be psi of J is going to be K. I'm going to call this one psi of G. All I know is that it's an element of G sent through psi, so it has to land in H, so it's some H. And this one is H inverse. Okay, this is actually the same as psi of G, psi of J, psi of G with the inverse outside because of another property we just proved. So this third term is H inverse. So what I get is H, K, H inverse. But now you see this element is in H, and this element is in K, and this is a conjugation by an element of H. But K is normal in H, and therefore this is in K because K is normal in H. Great. So what that tells me then is that G inverse is in J, and therefore, since this was for any J and any G, that tells me that J is normal in G, as I wanted to prove. So that concludes the proof of my proposition. And now we're going to do some examples. Okay, so let's see some examples. Remember that we had a homomorphism psi that went from GL2 to R star. And let's see what happens, for example, if I send one of the properties we just proved is that if I have a group, a subgroup of GL2, the image should be a subgroup of R star. Let me take J to be the subgroup generated by the matrix 0, 1, 1, 0 in GL2. That matrix is actually an element of order 2. If you square that matrix, try it out, you get the identity. So this group is actually just the matrix itself and the identity. So I'm just going to write the elements. There's exactly 2 elements. Okay. And so what is psi of J? I just need to do psi of one element, psi of the other. The determinant of 1001 is 1, and the determinant of 0110 is -1. So this is, in fact, it is a subgroup under multiplication of R star is the subgroup generated by -1, and R star is a subgroup, as it should be, because we just proved it should be a subgroup. Okay, great. Now let's go backwards. Let's start with a subgroup of R star and send it back through psi and see what we get. So, well, I have a subgroup right here. So let me call K is going to be the subgroup generated by -1. So that is just plus or -1 as a subgroup of R star. And let's see what is, now I'm going to call it J prime, the inverse of K. Well, what is going to be this? This is by definition are matrices in GL2 such that psi of the matrix lands in K. What does that mean? Those are matrices in GL2, right? GL2 like this, such that the determinant of the matrix lands in K, but K is plus or -1, so the determinant is plus or -1. What do we get? Do we get just J? Do we get just these matrices? No, there is a lot of matrices that the determinant is plus or -1. For example, -1, 0, 1, or so. For example, in here are matrices like lots of matrices, -1, 0, 0, 1, or -1, 0, 0, -1, or 3, 3, 4, 2, that's 9, -8, that's 1, etc. There's a lot of matrices that are in there. So this is a very large thing, but it is a subgroup. So the matrices whose determinant is plus or -1, it's an entire subgroup of GL2. Moreover, R star is abelian. And remember that every subgroup of an abelian group is abelian, is normal. So any subgroup K in R star is normal. In particular, that subgroup plus -1 is normal in R star, and that implies that the subgroup of matrices in GL2 whose determinant is plus or -1 has to be normal in GL2 of the real numbers. Now, that is a new thing. We didn't prove this, I think, before. And coming up with subgroups, so as I said, if you have an abelian group, every subgroup is normal. But if you have something like this, which is non-abelian, coming up with normal subgroups is not a trivial matter, and it's not an easy way to come up with them. But here is now one we've constructed easily, a subgroup which is normal in GL2. Another example is, easier example is that the identity, the subgroup generated just by the identity inside R star, that is a subgroup, and it is in fact a normal subgroup. That is always the case for any group. The subgroup, the trivial subgroup just with identity in it, is normal, and that tells me that psi minus 1 of the identity has to be normal in GL2. What is this? These are the matrices in GL2 whose determinant is exactly 1. So that is normal in GL2, and that does have a name. The determinant, the matrices with determinant 1, that is called SL2 of R. That proves that SL2 is always normal in GL2. But as you can see, we actually have another one, and you can figure out many other subgroups of R star. Take a prime, like the prime 2, and look at the subgroup, multiplicative subgroup generated by 2 inside R star. So all the rational numbers that are powers of 2 and powers, positive and negative powers of 2. Look at the matrices whose determinant is a power of 2. That will be normal in GL2. Great. So now let me show you another example, a different example. Let's look at, let's prove that the alternating group inside Sn is normal. How are we going to do that? What I want to show you is that the AN is actually it has to be some sort of coming up from one of the homomorphisms, one of the properties of the homomorphism. So this fact that we actually came up with here, that works in general. So let's prove that corollary first. Let psi from G to H be a group homomorphism. Then psi minus 1 of the identity in H is a normal subgroup of G. That comes from the fact that simply this is always normal in H, and therefore the inverse image of a normal subgroup is normal in G. That's the entire proof. And in fact, that normal subgroup is very useful. So that normal subgroup, in fact, it has a name because that is the kernel, the elements of G that map down to the identity. That is the kernel of the homomorphism. So let psi from G to H be a group hom. The kernel of psi is those elements in G such that psi of G is the identity in H. That's how we define the kernel, and what we've just proved is that the kernel of psi is always a normal subgroup of G. Okay, so we're going to use this to prove that AN is normal in Sn. And how are we going to do this? We're going to come up with a homomorphism such that AN is the kernel. So let me show you how to do that. So here I'm going to come up with a map from Sn to mu2, which is plus or minus 1, which is simply isomorphic to z modulo 2z, that sends sigma to 1 if sigma is an even permutation, and to minus 1 if sigma is an odd permutation. Remember that sigma is even, respectively odd, if sigma can be expressed as a product of an even, respectively odd, number of permutations, number of transpositions rather, and that is actually a homomorphism. Psi is a hom. Let's see why. First of all, it is well defined. Remember that we had a theorem that if a permutation has an expression as a product of an even number of transpositions, any expression respects the same parity. So that is going to be tell me that this map is well defined. And now, how do I prove that this is a hom? Let's see how much is psi of sigma tau, of the product of two permutations. This is going to be, well, first of all, if both sigma and tau are both even permutations, then each one has an expression as an even number of transpositions, and the product of the two expressions will also have an even number of transpositions. So that will give me a 1. But that is 1 is 1 times 1, and that is the same as psi of sigma times psi of tau in that case. If sigma is even and tau is odd, then I get a -1. I have an expression for sigma as an even number of transpositions, followed by an expression for tau as an odd number of transpositions. In total, I will get an odd number that is -1 times 1. That is also sigma, psi of sigma times psi of tau. If sigma is odd and tau is even, I still get a -1 as a 1 times -1, and it also satisfies the property I want. And if both sigma and tau are odd, then I get a 1 as a product of -1 times -1. Great. So it is a hom, and now what I can, once I know that this is a hom, then the kernel is normal. So the kernel of this map, which is usually called by the way the sign map of Sn, the kernel is going to be normal in Sn. But what is the kernel? The kernel of will be permutations in Sn such that psi of that permutation is 1, which is those permutations in Sn such that the sign of sigma is 1, which is those permutations in Sn such that sigma is even, and that is precisely how we defined An. Thus, we have proved that An is normal in Sn as we wanted to prove. Okay, very good. So next time, we're going to introduce the concept of the first isomorphism theorem through some examples of homomorphism. So we'll do that as an introduction, and then from there, we'll move on to actually proving what we call are the isomorphism theorems.